Why does your tire pressure rise when you drive? And how can one equation predict how a balloon, an engine, and your lungs behave? In this video, you'll learn 3 core gas laws: Boyle's laws, Charles' laws, and the ideal gas law. And then after that, we're going to learn how to solve real problems using pressure, volume, temperature, and moles. Moles, before we start, it's like a way to count molecules and atoms and things like that. It's like saying a dozen. It's how we measure big quantities of very small stuff like atoms and molecules. And 1 mole is equal to 6.022 times 10 to the power of 23 elementary entities. So this could be made up of atoms, molecules, or ions. And this number is known as Avogadro's number. It's famous. It's on the free cheat sheet in the description if you want to use it. First law we'll look at is Boyle's law. So Boyle's law is pressure versus volume. It says that pressure multiplied by volume is constant at a constant temperature. This is kind of like energy conservation. What does this mean? It's always constant. That means if pressure goes up, to keep the total value the same, volume must decrease. Same the other way around. If volume goes up, then pressure has to decrease so that the total value stays constant. Next law is Charles' law. Charles' law relates volume and temperature. So volume and temperature is constant at constant pressure. T here represents the absolute temperature in K, which is Kelvin. This says that volume increases as the gas heats up because the ratio has to stay the same, right? So if the temperature is increasing, then the volume has to go up as well for it to stay constant. The final law relates pressure and temperature, and it's called the Gay-Lussac's law. It says that pressure divided by temperature is also constant when it's at a constant volume. So you can kind of see all of these are related in some way. Temperature, pressure, volume. This says that pressure increases when a gas heats up inside a fixed container. So this applies when the volume is constant as well. So that means, in English, the pressure will increase if the gas heats up inside a fixed container, like a tire. All of these laws we've gone through are all special cases. Now we roll them all into one general equation called the ideal gas law. This core equation is going to be seen a lot in the problem solving part of this video. So if you want to remember, it's in the free cheat sheet in the description. So it's P, pressure, times volume equals N, which is the number of moles, multiplied by R, which is a gas constant. I'll look at that soon. Multiplied by the temperature in Kelvin. This is your master formula. It connects everything: gas, temperature, volume, and pressure all in one. The gas constant is 8.314 joules divided by mole times Kelvin. Just like all other constants like the gravitational constant or Avogadro's number, this number, you don't need to memorize it. You can just Google it. And usually you'll write it as R. You won't really substitute it in unless you need an exact number. There's something called STP. STP is the standard temperature and pressure. So T is equal to 273 Kelvin. And P is pressure equal to 1.0 times 10 to the power of 5 pascals. At STP, 1 mole of any ideal gas is 22.4 liters. So STP conditions, keep this in mind when we do our problem solving later on. And when would you use this version of the formula, this master equation? If mass is given, then you can convert it into moles using this equation. N equals mass over molar mass. So when using that formula, always convert temperature into Kelvin from Celsius or Fahrenheit, whatever. Convert volume to meters cubed, and pressure, convert it into pascals, because these are what's used in the standard global SI system for science. Before we do our problem solving, let me show you some stuff with the formula. For the ideal gas equation, you can solve for any unknown by rearranging with your math skills. So you can solve for pressure by itself, you can isolate temperature. This is going to be useful. And when a gas changes state, you use this thing. It's called the combined gas law. P1 times V1 over T1 is equal to P2 V2 over T2 if N is constant. This is just like one of those energy conservation equations. This handles questions like, what happens if I double the temperature but I cut the volume in half? Now you're ready to solve some problems with me. And here's the situation of the problem. You have a small gas canister because you're camping and you're cooking stuff. It contains exactly 1 mole of propane vapor. so gas, and it's measured at standard conditions. We're asking how much space does the gas occupy inside this canister. So standard conditions is 273 Kelvin and pressure being 1.01, 10 to the power 5 pascals. The ideal gas law is what we're going to use, which is PV equals nRT, and we're going to rearrange for volume because that's what we're looking for. This gives us a formula V equals nRT over P. Being able to rearrange your formulas fast is very useful in physics. So find a way to get good at that. And for reference, the gas constant, 8.314. So we know everything here. We know R, we know the temperature, we know the pressure. And here's what's interesting. We know N, because N is the amount of substance in moles. And 1 mole is equal to Avogadro's number, this amount of molecules. And it says 1 mole of gas, so that means N is equal to 1. We're being told how much gas is present. In this case, it's not something we calculate, it's just given data. So if you had 1 mole of nitrogen, 1 mole of helium, or any other ideal gas at STP, you would always use N equals 1 in the ideal gas law. So let's substitute. The volume our gas takes up is equal to 1 for N. We plug in R, we plug in the temperature, divided by the pressure. In meters cubed, it's roughly 0.0225 meters cubed, and this equates to 22.5 liters, because gas can be measured in liters. So that's the volume of the gas in our canister. That's how much it expands to at the standard STP conditions. That's more than a basketball. Problem number 2 we'll go through is a balloon at a kid's party. So a helium balloon at a birthday party, let's draw it. It has a radius of 14 centimeters. It's filled at room conditions of the pressure being 1.00 times 10 to the power 5 and the temperature being 293 Kelvin. The molar mass of helium, is 4 grams per mole. We're looking for the mass of helium inside this balloon. How do we approach this? First, we need to find the volume of this. So let's use a circular volume formula, which is 4 over 3 pi r cubed for a sphere. This is volume of a sphere. The radius is plugged in as 0.14 meters, giving us roughly 0.0115 meters cubed of space inside the balloon. Now we're going to use the ideal gas law to find moles. So we can rearrange for N from the ideal gas law formula to find the amount of moles. And let's plug in all our stuff. So P, the pressure of the room, 1.00, 10 to the power 5. The volume we just found, put that in, 0.0115. Next is the gas constant, 8.314, and the temperature, which, as stated at the beginning, 293 Kelvin. We plugged in all our numbers, so this equates to 0.472 moles. 0.427 moles, nice. We know N, the number of moles. Next, we have to convert moles into mass. So if you remember the N equals mass divided by molar mass formula, we can rearrange this for mass by multiplying both sides by molar mass. So you get mass equals N times molar mass. We know N is 0.472, and molar mass for helium is 4. This is 1.89 grams. That means inside this balloon there's 1.89 grams of helium. And the big picture idea is you see what you're given, and then you use the ideal gas law or whatever equation fits best. You solve for the unknown you're looking for, and you use the formulas to link together everything that you need. Second last problem we'll go through in this video is how much air is in your bedroom. The goal is to estimate the mass of air inside a standard bedroom using gas law reasoning. So you're standing in your room, and your room, let's draw it out. That's your bedroom here. You got nice windows, got a nice bed. So the dimensions of the room, the length is 5 meters, the width is 4 meters, and the height is 2.4 meters. So that means we already know the volume. The volume being 5 times 4 times height, 2.4, is 48 meters cubed. And we're going to assume a few things. We're going to assume that air behaves ideally. we're going to assume that room temperature is 20 Celsius, which in Kelvin is 293. And we're going to assume that the pressure is 1.01 times 10 to the power 5 pascals, and that the molar mass of air is 29 grams per mole. Let's find the amount of air in your room. So we're going to use the ideal gas law to find the moles. Again, with the rearranged for N variant, N equals PV over RT. We can plug in our values. So P, and then the volume, divided by R, which is gas constant, times the temperature. This is roughly 1,990 moles. Now we can convert moles into mass because we know that N is equal to 1990. We do the same thing. Mass is equal to N times molar mass, which is 1090 multiplied by the molar mass 29, giving us 57.7 kilograms of air inside of your bedroom. That's like having a person worth of weight floating around you invisibly. The final problem of this video is related to tires. So your car tire is this thing, and it's full on a cold morning at 12 degrees Celsius. The gauge pressure, so you measure it with one of those car gauge things, it reads 220 kilopascals. Later in the day after driving, the air inside the tire heats up to 42 degrees Celsius. Assuming three things: the tire volume doesn't change, no gas escapes, the atmospheric pressure is 101 kilopascals. Find the new gauge pressure after you drive. And I think I mentioned this in one of my fluids videos, but gauge pressure ignores atmospheric pressure. So we have to work with absolute pressure by adding them both up. And then at the end, we're going to convert it back to gauge pressure. So step one, what are we looking for? Looking for gauge pressure after the temperature changes. The ideal gas law doesn't fit as well here. We're going to use the constant volume gas law, which we looked at earlier on in the video, which says that the ratios between pressure and temperature is always constant. Here's what we know. Temperature is in Kelvin for these kind of equations, but we're given it in Celsius, so let's convert. Temperature 1, so when it's 12 degrees, is 12 plus 273, giving us 285 Kelvin. By the way, that's how you convert to Kelvin. Temperature at the second time is 42 degrees, which is 42 plus 273, giving us 315 Kelvin. Next, we need to find the pressure before our driving session, so on the cold morning. This is 22 kilopascals from the gauge, added with the atmospheric pressure that we didn't consider, giving us an absolute total pressure of 321. So that's our P1 value. Lastly, all we're looking for is P2. But since we know everything, we can simply isolate P2 from this formula, giving us P2 equals P1 multiplied by T2 over T1. This is P1, and we know everything here. P1, 321, multiplied by T2, which is 315 Kelvin, divided by 285 Kelvin. The answer, roughly 354.4 kilopascals, but we're not done yet. This is the absolute pressure, the total pressure. We're looking for gauge pressure, which doesn't take into account atmospheric pressure. So take this value, subtract 101 from it, and we find that the gauge pressure is 253.5 kilopascals. What does this mean in the context of this problem? It means the gauge pressure went from 220 to 253, which is about a 15 pressure rise just from driving and the heat.